probability density function. So it's taking the same types of information, but changing how the question is asked. So before, the question was always, what percentage of the population meets this requirement? Now we're going to be asking, what's the probability that this thing will occur if an independent variable is picked at random? So if we're asking you for the probability that something happens, we're equivalently asking you what percentage of the population has this characteristic. So let's look at a problem and see the difference in wording, and then compare that to what we already know how to do, just so we can be sure that we're answering the right questions. So, example 5. Suppose the heights of students in a class are measured and recorded in the following table. So, 4 of the students in this class are 5 foot 6 inches. 6 of the students in this class are 5 foot 8 inches. 6 are 5 foot 10. 5 are 6 feet. 2 are 6 foot 2, and 2 of them are 6 foot 4. It's a pretty tall class. So first I want to know what percentage of students are less than 6 feet tall. Now, what we need to know in order to solve this type of problem is how big our population is so that we have a way to represent 100% of the population. So what I'm going to do is I'm going to add up the total number of students. So 4 plus 6 plus 6 plus 5 plus 2 plus 2. And that's going to give me 25 total students. Now, what I want to do is figure out how many of those students are represented in the question I'm asking. So A says, what percentage of students are less than 6 feet tall? So remember, when we talk about less than, we're including everything up to, but not including 6 feet. So that means we're including the students who are 5'6", 5'8", and 5'10". So the number of those is 4 plus 6 plus 6. So 16 out of 25 are less than 6 feet tall. If we turn that into a decimal, we get 0.64, which means that 64% of the students in this class are less than 6 feet tall. So this is what we were doing before, determining what fraction of our population meet a particular requirement. So the way we can turn this into a probability problem is by just rewording the question, even though the way we calculate it is going to be the same. So part B says, if a student is picked at random, what is the probability that they are at least 5 foot 10 inches? So that means we are picking someone at random out of this group of 25. And so the probability is going to be the fraction of the population that represent this characteristic. So at least 5 foot 10 means that we're going to be doing 5 foot 10 and above. So at least 5 foot 10, there is 6 plus 5 plus 2 plus 2 students. So that means 15 students are represented in this population. So 15 out of 25 is going to give me 60%. So 0.60 or 60%. So since 60% of this population meet this requirement, that means if I were to pick one student at random, there is a 60% probability that they will be at least 5 foot 10, because that is the fraction of the population that has that characteristic. For part C, we want to create a table that's going to give the heights of the students and the probability that if they were picked at random, that they would be that height. So what does that look like? So in order to create a table that's going to give us our probability or our density, what we need to do is we need to take each height and figure out what proportion of the population that represents. So for example, for 5 foot 6, there are 4 students in this category. So what we need to do is figure out what 4 out of 25 would represent as a fraction. So 4 out of 25 is going to give me 0.16. So if I were to pick a student at random, there is a 16% chance that that person would be 5 foot 6 inches. For 5 foot 8, we want to do 6 out of 25, which is 0.24. Same for 5 foot 10, 6 out of 25, which is 0.24. For 6 feet, we'll do 5 out of 25, which is 0.2. For 6 foot 2 and 6 foot 4, we'll do 2 out of 25, which is 0.08. So notice, if you were to add up all those numbers, you would get 1, because this represents 100% of the population, which is one of our requirements for a density function. Notice also that the numbers we're working with are all strictly positive, also a requirement. So now we have a probability density function that represents the probability of picking someone at random, which also is the same as talking about the percentage of the population that has this particular characteristic, which is exactly what we were doing before. The difference is in the wording, in that now instead of asking what percentage of the population, we're asking what is the probability that if one of these items is picked at random, it's part of this group, which is the same thing as asking for the fraction of the population. So now we are able to talk about probabilities because we know how to find these fractions of the population. Let's look at one more example that's going to bring back our density functions, but also talk a little bit about probability. Example 6. Which of the following is the most likely to represent the probability density function for the time t in minutes that the next customer walks into a store? Assume that minutes start at time equals 0. So we start measuring at time equals 0, and we're watching the door, and we're trying to figure out which of the following is going to be the probability function, the PDF, the probability density function, that models when the next customer will walk in the door. So remember, because we want this to be a density function, even though we're still talking about probability, we need our requirements to hold. So first, we need to look at the functions and first make sure that they're always positive. So notice that A is cosine of t, and it's defined for 0 to 2 pi. Well, if you think about cosine, cosine starts positive, but then it goes below the x-axis before it comes back up. So there are values here that are negative. Therefore, this cannot be our probability density function because it has negative values. And to be a density function, all values would need to be positive. So it's not going to be A. B, C, and D, however, all are strictly positive. So therefore, they're still in consideration. Another consideration we have is that when we integrate our function over the bounds, it has to equal 1. So if you check, B and D will both integrate to 1 on their bounds. So for B, we would do the integral from 0 to infinity, because t is just greater than 0. And for D, we would do the integral from 0 to 4. C, however, we'll do out real quick. When you integrate that from 0 to infinity, because t is greater than 0, e to the negative 3t dt, what happens is you get e to the negative 3t divided by negative 3 from 0 to b. Remember, when we do improper integrals, we're going to use a b. So when we plug in the upper bound, we're going to get negative 1 over 3e to the 3b. I brought that term down, minus negative 1 over, and now we'll have 3e to the 0. And we want to look at what happens as b goes to infinity. Well, as b goes to infinity, the first term goes to 0, and the second term is going to go to 1/3. So when we do that, we get 1/3. 1/3 does not equal 1. Therefore, C is not an option. Does not integrate to 1. I'll leave it up to you to check that both B and C integrate to 1 over the bounds given. However, we now need to determine which one is the more likely scenario here for our customer. So let's talk about the distinction of what these say. B says that there's a high probability, if you graph this, right, all the area is front loaded. So there's a pretty high probability that someone's going to come in between, say, 0 and 3 minutes, 0 and 4 minutes, 0 and 5 minutes. But the probability just slowly declines forever and ever, which means it could be 20 minutes after you're looking at the door. It could be 45 minutes, right? The probability is really low, but the probability exists. Okay. And again, that's because when you look at the picture, I'll show you a quick picture of B, right? Exponential decreasing function, right? The probability gets really, really small over here, but it still exists. Okay. Now D has a probability of 1/4 from 0 to 4 minutes. So 1/4 is here, right? Which means that the probability that that customer walks in after 4 minutes is 0, because it's only defined from 0 to 4. Anything outside of that is just 0. And that doesn't really make sense, because it's certainly believable that after 7 minutes is when the next customer walks in, right? And there's nothing to allow for that when we're restricted from 0 to 4. Therefore, the most likely density function, probability density function here, is going to be B, 3e to the negative 3t. It's positive, it integrates to 1, and it allows for any amount of time to pass before the next customer walks in.